We're more than halfway through the chapter, so I'm pretty sure that we can finish that on the first hour of the day. And in the second hour, I will move to the next chapter, which is the steam system. Okay. Oh, Pak Hendra, I'm not able to share.
Oh, okay, Pak Miki, I will change the setting, please.
Okay. Okay. Right. So what we're learning today is sort of the more auxiliary topics in steam turbine. But before that, oh, where is it? There we go. So we finished off here last week, right? So we've discussed about the steam rates and how to calculate them. So it is really important to know what an actual steam rate is, what a theoretical steam rate is. Actual steam rate is whatever your instrument is telling you. Okay, so it is always higher than theoretical steam rate because of all of these different types of inefficiencies in the turbine or energy losses in the turbine. So okay, ASR is always higher than TSR. And if you imagine that you're looking at the data that is churned out by your process plant's instrumentation, then what you're seeing there is the actual steam rate. Okay, so don't get confused by the examples in the diktat. Okay, so it doesn't mean that you need to know the TSR first and then know the efficiency to calculate the ASR. Depending on the situation, you might actually already have the data to calculate ASR and then calculate the TSR based on the thermodynamic principles and then calculate the efficiency as the final quantity. So it really depends on the problem. Okay. All right. Now we're just gonna gloss over this the second parameters, which is called heat rate. Okay, so steam rate and heat rate is different. Heat rate refers to specific heat consumption. So so it means that this must be calculated in terms of enthalpy change in steam exiting minus steam entering the turbine. Okay. Oh, sorry, this is the other way around. So steam entering the turbine, the enthalpy of steam entering the turbine minus the steam exiting the turbine. So that will be the heat that is converted into work in a steam turbine. Okay. So specific heat consumption is often used to express turbine performance, especially if the turbine is used only for producing electrical energy. Ya, jadi besaran specific heat ini, besaran heat rate ini lazim digunakan hanya kalau steam turbine-nya digunakan untuk produksi listrik. Kalau steam turbine-nya dipakai untuk memproduksi energi mekanik dan listrik, jadi misalkan if for example the turbine is used for dual purpose, so it's used for the purpose of generating electricity and also to drive other process equipment, then usually steam rate is more appropriate. Okay, so again, heat rate is typically only used for power generation, ya, pembangkitan tenaga listrik. Okay, so in PLTU, jadi di fasilitas PLTU itu yang digunakan adalah besaran heat rate ini, bukan steam rate. But in a typical, just a general process plant, then we typically use steam rate. Yeah. So if you look at the unit of HR and also how they're calculated is quite obvious. Okay, so for example, gross heat rate or gross specific heat consumption is calculated by taking the ratio of total enthalpy change, total enthalpy of steam entering the turbine, yeah, divided by the gross electricity output. Now take a look at the peculiarity here. So the quotient, bilangan pembaginya ya, the quotient is gross electricity output. So we're no longer talking about mechanical energy in general, but we're talking about electricity output. Okay.
Sure.
So if your turbine is not connected to an electrical generator, then you cannot calculate HR, heat rate. Ya, jadi dari rumusnya jelas ya, bahwa bilangan pembaginya adalah daya listrik, ya, daya listrik yang dihasilkan. Jadi total entalpi masuk dalam steam, ya, dibagi daya listrik yang dihasilkan. Jadi kalau turbinnya nggak dipakai untuk menghasilkan listrik, ya ini nggak bisa dihitung. Ya. Okay. But ASR, on the other hand, okay, ASR and TSR, you can calculate those numbers on any steam turbine. Okay, not just the ones that generate electricity, but any steam turbine, you can calculate the steam rates. Okay. Okay. And here, what gross electricity output refers to is before subtraction with power plant's internal uses. Okay. So now imagine yourself looking at these steam power plants at night, okay, preferably at night. So you can see that they have lightings everywhere in the PLTU. Okay, so if you drive by PLTU Python at night, then of course you will see lights everywhere. You can also imagine that they need electricity to operate their own machineries. They have their own instrumentation that requires electricity. So we call that power plant internal use. Ya, jadi kalau kalian membayangkan PLTU, ya, itu kan pasti mereka butuh listrik juga, ya, untuk mengoperasikan sistem penerangan, sistem instrumentasi, untuk menggerakkan mesin-mesin mereka yang lain, gitu ya. Jadi pabrik pembangkit listrik itu sendiri juga memerlukan listrik, ya, untuk penggunaan mereka sendiri. Nah, gross electricity output ini adalah listrik, daya listrik yang dihasilkan yang keluar dari generator. Okay. So this is measured at the generator output point before we consume some of the electricity for the power plant's own use. Okay, that's called gross electricity output, right? Now, when you subtract the electric power consumption by the power plant itself from the gross electric output, then you will get a net electricity output. Okay, and if you use that to calculate the heat rate, then what you're getting is net heat rate. Okay, so net heat rate is total heat enthalpy, meaning total enthalpy in steam entering the turbine divided by net electricity output. Okay, so there's a more complete explanation here. So electricity own use by a power plant includes, for example, boiler feed water pumps, air blower. Air blower is a big. This consumes a large quantity of electric power. Okay, solid fuel conveyor. Okay, coal conveyor for coal, for biomass, whatever. Powerhouse lighting and so on. Okay, so all of these consumptions are for the power plant's own operation. Okay, so when you take that out from the gross electricity, what you get is net electricity output from your electric generator. Okay, right? I think that's pretty clear. Now, the next one is PNHR. Okay, power plant or plant net heat rate. Okay, so if the heat consumption is based on energy input to the boiler, okay, then the overall heat consumption in power plant system requires calculation of boiler efficiency. So we're taking this analysis one step further, one step back. Okay, what is the difference between this one and the previous one? In the previous one, the energy input is the steam, the inlet steam enthalpy to the turbine. Okay, so in GHR or NHR, we disregard. Okay, we ignore the energy losses or the energy consumed by the boiler. Okay, jadi perbedaan antara PNHR dengan GHR dan NHR adalah yang sebelumnya tadi itu energi inputnya sudah berbentuk steam, sudah berbentuk enthalpy steam. Kita abaikan energi yang habis di boiler. Yeah. But here, we're taking into account the energy that is converted in the boiler. Okay, so the heat consumption is based on energy into the boiler, meaning energy contained by the fuel that's going into the boiler. Yeah. So plant net heat rate is calculated based on fuel combustion heat in boiler. Okay, so heat generated by the fuel combustion in the boiler divided by the net electricity generation output. I think output is more appropriate than outflow actually. Okay. Right. So we call that plant net heat rate. Why? The reason why we use the word plant is because we're expanding the control volume, okay, to include the boiler as well. Previously, we exclude boiler. Now we're including the boiler. Yeah. Okay. So of course, PNHR has to be higher than NHR, okay, or GHR. Okay. And the correlation between PNHR and NHR is as follows. Then, so we insert this, we plug in the number, the boiler efficiency number, and we also plug in the percentage of power that is used by the plant itself. That's not a good word of, not a very good wording. So power consumed by the for power and own use. There you go. Okay, as a fraction of gross produced power. So it's not it's fraction of the, there you go, gross produced power. Yeah. Again, gross produced power is measured at the output of the electric generator. Ya, jadi gross produced power ini diukurnya di titik pengeluaran listrik dari generator. Ingat ya, boiler menghasilkan steam, the steam drives the turbine drives the generator, and the generator generates electric power. So if you measure the power right at the output of the generator, what you get is the gross power, gross produced power, right? And if you subtract out the electric power that is consumed by the plant itself, the remaining is net electric power or net electric output. Yeah, I think that's, you know, that makes sense. And by the way, you can easily imagine this using a Sankey diagram. Okay, so please familiarize yourself with how to construct and how to read a Sankey diagram. Yeah, diagram Sankey. Yes, Kevin.
Sir, I have a question, sir. Can you hear me?
Yeah, that's fine.
Sir, you said just now that the net electricity that is not used by the plant, what will it be used for, sir?
Okay, if the plant is a PLTU, is a power plant, then the electric power goes to the power grid. Yeah, it goes to whoever consumer is the client of this power plant. Now, for example, let's say that this power plant is supplies its electricity to an adjacent chemical processing plant. Okay, so the net power will be the amount of electric power that is transferred to the process plant. Yeah. And another example is, you know, like facilities like Python power plant or the Kerawang power plant. Okay, so any power plant that burns coal or hydrocarbon fuel. Okay, so any remaining remaining electric power that is not consumed by their own gets exported to the PLN's grid. Okay, ya. Jadi yang namanya produksi listrik neto itu adalah yang diproduksi di luar kebutuhan pabrik sendiri, di luar kebutuhan power plant ini sendiri. Nah, tentu saja diharapkan yang bisa diekspor keluar ini jauh lebih besar daripada yang dipakai oleh power plant. Otherwise, it's not a power plant. Okay, so you know, it makes common sense that if you draw this in a Sankey diagram, for example, that the amount of exported export, meaning it goes outside of the control volume. Okay, I'm not meaning that export in a national sense. Okay, So the remaining electricity that is exported outside the control volume of the power plant supposed to be larger, much larger than the amount of electricity that they consume themselves. Yeah. Okay. I hope that gives you a pretty clear picture. So, and where does that power goes? Yeah, it depends on the application of the power plant. If the power plant is designed to produce electricity per se, then it goes to the grid network. Yeah, dijual ke PLN. But if this power plant is built to serve a chemical processing plant, then that net electricity production will go to the process plant. I'm giving you one example, the one that I remember. This is hang on a second. Let me rack up my memory. Yeah, PT Badak, for example. Okay. So each process train, okay, each process plant in PT Badak's LNG liquefaction, they have their own boiler, they have their own power plant. Okay, they have their own steam turbine. Now, the steam turbine in one train in LNG Badak produces more electricity than what is necessary to drive the refrigerant compressor. Okay, so this excess electricity then goes to the power plant, to the process plant itself. Yeah, for various uses. For instrumentation, for other process machineries, for other pumps, compressors, and so on. Ya, jadi contohnya di PT Badak. Ya. Mungkin masih ingat dari diskusi kita minggu lalu, PT Badak itu memiliki 8 jalur, namanya train, oleh kereta api. Okay. So each train in Badak itu mempunyai satu boiler sendiri, memiliki satu PLTU sendiri. Ya. Nah, listrik yang dihasilkan oleh energi yang dihasilkan oleh boilernya PT Badak ini itu utamanya digunakan untuk menggerakkan, it's primarily used to drive a big steam turbine. Okay, and the big steam turbine is used to drive gas compressor, refrigerant compressor. Jadi konsumsi terbesar dari energi steam yang dihasilkan di boiler PT Badak ini adalah untuk menggerakkan turbin. Turbinnya menjadi prime mover bagi kompresor, ya, kompresor refrigeran. Nah, energi yang dihasilkan oleh turbin uap ini, oleh turbin kukus ini berlebihan. Ya, kalau hanya untuk menggerakkan kompresor itu kelebihan. Nah, kelebihannya dikemanain? Kelebihannya digunakan untuk menggerakkan equipment yang lain, digunakan untuk membangkitkan listrik. Ya, sebagian listrik yang digunakan di pabrik itu dibangkitkannya dari turbin steam tadi, turbin steam yang besar itu. Gitu. Ya. Okay. So, but that's not a power plant. So that's not a steam powered. That's not a power plant in a narrow sense. Okay. A power plant in a narrow, in a more restricted sense, is PLTU Python, because PLTU Python is designed to produce electric power above all else. Okay, PLN didn't build PLTU Python to drive compressor, for example. Okay, but it is solely used to generate electricity. That's its main business, is to generate electric power to be sold into PLN's electrical grid. Ya, jadi kalau yang PLTU Python itu produk utama dari PLTU-nya adalah ya listrik itu sendiri. Ya, jadi PLTU Python itu tidak dirancang untuk menggerakkan, mentenagai pabrik yang lain. Tetapi ya dia itu pabrik utamanya. Produk utamanya adalah listrik. Listrik yang dihasilkan oleh turbin uap dan generator listrik ini, setelah dikurangi dengan kebutuhan pabriknya sendiri, which is itu jauh lebih kecil daripada produksi gross-nya, kemudian ditransmisikan ke grid, ke jaringan PLN. Okay. So you can start to see, hopefully you can start to appreciate how diverse this process utility design is. Okay, it really depends on what you want to do with the utility system. Do you want to run them as a standalone utility plant, or will it be integrated to chemical processing plant nearby, or even integrated intimately. Okay, it's purely it's fully integrated with the chemical processing plant as well. You can all have all sorts of variations. Okay, in when it comes to utility plant design. Okay, now let me move on. If you guys have any questions, just feel free to interrupt me. Okay. All right. Specific heat consumption. So what are the factors influencing specific heat consumption? So we have, for example, a decrease in condenser pressure will reduce NHR. Okay, if we can somehow reduce the condensation pressure, that will reduce the heat rate. Okay, that will, well, effectively, it will increase the efficiency of the power generation. However, do keep in mind that if you reduce the condenser pressure, then your boiler feed water pump will have to work harder, okay? Because then you need a higher pumping ratio, okay, from condenser to boiler pressure, okay? So remember our lesson last week, yeah? So higher boiler pressure will increase thermodynamic efficiency, right? Conversely, if we reduce the condenser pressure, okay, so if we reduce the condenser pressure, that will also improve efficiency. That will reduce heat rate, but at the expense of of needing more power on the part of the PFW pump. Okay, so there's always compromise in everything, in almost everything. Steam temperature entering the turbine. Preheating combustion air before entering the boiler can also reduce specific heat consumption by 2%. And actually, this combustion air preheater is a very, very common accessory to a boiler. Hang on a second. Let me check on some. All right, I'm back. Sorry, there's something that I need to look at a few minutes ago. Okay, where were we? There we go. Reheating combustion air. Okay, so this is actually a very good way of a very common way actually to improve the thermal efficiency of boilers, steam generation system. Okay, and the way that this is practiced in the industry is by the use of what is called an economizer. Okay, so if you remember our discussion on boilers, so an economizer is a heat exchanger whose purpose is to preheat the combustion air before entering the boiler. Okay, now that can reduce specific heat consumption by 2%. Now 2% might not sound much, but if you multiply this with with gigajoules of heat generation or heat consumption consumed by the boiler every day or even every hour, then the 2% actually is multiplied by a very large number, and eventually it will become a very significant dollar amount. Okay, otherwise people will not make economizers, right? Yeah. Okay. Is it economizer? No, actually, it's not economizer. It's yeah, it's air preheater. Economizer is the one that is the heat exchanger to increase the temperature of the BFW. Ya, jadi apa namanya? Salah satu hal yang bisa menurunkan konsumsi panas dari sistem boiler dan steam turbine ini adalah memanaskan combustion air. Ya, jadi ini boiler ya, kita bicara boiler, bukan steam turbine. Oke. Jadi dan ini sebetulnya sudah sangat lazim dilakukan. Ya, ada dua yang bisa dilakukan. Jadi apa namanya, memanaskan udara sebelum masuk ruang pembakaran dan juga memanaskan boiler feed water sebelum masuk ke dalam boiler. Ya, dua-duanya ini bisa mengurangi specific heat consumption. Dan dua-duanya ini adalah langkah-langkah penghematan energi yang sudah sangat lazim dilakukan di dalam boiler. Ya. Oke, mungkin kalian melihat, oh ini penghematan cuma 2% ya, tapi 2% ini kalau dikalikan dengan total panas yang dikonsumsi atau dihasilkan oleh boiler, ini luar biasa. Ya. Dampak dolarnya luar biasa. Ya kalau nggak memang beneran bisa menghemat, ya ngapain orang bikin air preheater dan juga economizer kan ya. Gitu. Jadi meskipun kelihatannya kecil, tapi 2% ini dikalikan dengan sesuatu yang luar biasa besar. Right. Lastly, pressure drop in the boiler on the steam channel can also affect specific heat consumption. Okay. Included in this group are factors that influence turbine efficiency. In other words, we want to have a clean channels. Ya, kita ingin apa namanya, perpipaan penyaluran steam yang bersih, yang mengurangi pressure drop. Ya, because any pressure drop will have to be compensated by extra power from the turbine. Yeah. Okay. And you can see more about this effect of condenser pressure and turbine load to turbine NHR, and also steam pressure to NHR. Yeah. There you go. Yeah. So higher condenser, which one is condenser pressure? This one, okay. So higher condenser pressure, so going from here to here to here, then you can see that we increase the turbine heat rate. So higher condenser pressure consumes more energy. Okay, more energy in the turbine inlet heat rate. Okay, so we want to have the condenser pressure as low as practically achievable. Okay, if the condenser pressure is too low, then your BFW pump will have to work harder. So there has to be an optimum somewhere. Okay, so low condenser pressure is good up to a point, right? That's another way of saying it. And then the turbine net output. Okay, so the higher the turbine net output, usually the lower its efficiency becomes. Okay, for the what does this one mean? Throttle flow rate. This one is a little bit confusing. Anyway, okay, let me put it this way. So the higher the turbine net output is, it requires. I'm not sure how to read this thing actually. Turbine net heat rate is. Yeah. Okay. Better. Okay. Here goes. Let me explain it in a words that are easier to follow. Okay. So higher turbine output, meaning larger turbines. Okay. Larger turbines tend to be more efficient in terms of heat rate. As you can see, if we follow a single condenser pressure, for example, take this one for example. Okay, 3.5 inch mercury of condenser pressure. If we increase the turbine size, meaning we will also increase its net output. Okay, and you can see that the turbine inlet heat rate, okay, net heat rate decreases. So bigger turbines tend to give us higher thermal efficiency than smaller ones. Okay, and this kind of behavior happens to a lot of is exhibited by a lot of process equipment. In fact, in general, the general rule of thumb in process industry, when we design a chemical processing plant, rather than having two small equipment, it is usually more economical to have one big equipment. Okay, that also applies to steam turbines. Yeah. So this is what this monograph or this graph is telling you, is that larger turbines tend to be more energy efficient. Okay. Now I'm not going to go through this problem example. We can go about this in a tutorial session. And Pak Hendra, do you already have a teaching assistant for this class?
For this class is Zeva, Pak.
Okay. Yeah, we can ask Zeva to go through this problem example. I want to cover as much theoretical material as possible and leave the problem examples and problem exercises to the assistant. Okay. All right. Okay, so it's pretty straightforward actually. I know it's as long as you know the meaning of heat rate, you should have no problem in working out this problem with these examples. Okay. Now the next part is talks about control system for steam turbine, and this is not a highly critical issue, so I'm just going to go through this rapidly. So control mechanism in steam turbine is also called power governing. Okay. Power requirements, in this case, it can be mechanical or electrical energy in a process plant, usually change over time. So in other words, our steam turbine needs to have the ability to decrease or increase its load, right? Turbine load also changes, requiring a regulated steam rate. So when the load increases, then the steam rate has to follow that load, so the steam rate has to increase, and vice versa. When the turbine load decreases, okay, for example, the power consumption from the process plant decreases, then the steam rate also have to decrease. Okay, now load changes results in changes in turbine performance. Okay, internal efficiency, specific steam consumption, and also heat consumption. Okay, so thermodynamic efficiency, you know, the letter eta, okay, huruf eta itu ya, huruf Yunani eta. So efficiency of the turbine depends on its load. Okay. So we need to expect that if we change the load of a steam turbine, that its thermodynamic efficiency will also change. Its specific steam requirement, steam consumption will also change. Ya. Ini berlaku untuk kebanyakan mesin, bukan hanya steam turbine. Ya. Jadi di mana kalau beban mesinnya diubah, ya, dimanipulasi, maka efisiensi termodinamik dari suatu mesin, termasuk turbin uap ini, itu akan bergeser. Ya. Oke, karena efisiensi termodinamiknya berubah, maka konsumsi kukus spesifiknya, jadi how much steam is being consumed per kilowatt hour of power generated, for example, that will also change. Okay. this behavior is actually ubiquitous. Okay, so for example, your motorcycle or your automobile, they also behave the same. Ya, jadi banyak sekali mesin industrial maupun mesin otomotif itu kelakuannya kayak gini. Jadi kalau bebannya diubah, efisiensi bahan bakarnya, efisiensi termodinamiknya pun juga bergeser. Ya, just as a side story, okay. I like automotive. Okay? I like reading about automotive technology, about cars, about motorcycles and stuff. So most 4-cylinder engines, yeah, that almost a big majority of cars in Indonesia are have 4-cylinder engines. Okay, jadi kebanyakan mesin 4-silinder kendaraan bermotor, ya, mobil terutama ya, itu efisiensi termodinamiknya paling tinggi di kisaran 3000 rpm. Okay, so the maximum efficiency, thermodynamic efficiency of most gasoline engines. Now we're not talking about diesel engines, but gasoline engines, okay, car engines, is typically in the 3000 rpm range. If you run it's usually between 2000 to 3000, okay, 2000 3000 rpm. If you go slower or if you go faster than that, the thermodynamic efficiency actually decreases. Okay, so it means that driving your car really slowly doesn't mean that will give you better fuel efficiency. Okay, same as driving your car really fast. So the optimum speed is always somewhere in between, not too slow, not too fast. Yeah. All right. That is the reason why traffic jams actually reduce fuel efficiency quite a lot. Yeah. All right. Now, how can we adjust the load of a turbine? Okay, it is done by two types of. It's called governing. Yeah. So the term governing only applies to steam turbine. It doesn't apply to any other turbine. It doesn't apply to gas turbines, for example. Okay. So for steam turbines, we can do this. We can manipulate the load or the steam rate by using throttle governing or bypass governing. Okay. This one is throttle governing. Okay. So the vapor pressure from the steam channel is lowered by a throttling valve. Jadi ada valve yang mencekik atau menthrottle steam itu sehingga tekanannya berkurang sebelum masuk ke turbin. Okay. Right. And automatic opening of valve is controlled by a governor. This one is the governor. Yeah. This one. That adjusts itself to the turbine rotation. Okay. So there's a self-regulating system that creates a mechanism in which, if the steam rate is higher, then the governor will tend to close, and vice versa. If the steam rate is decreased, the governor tends to open. Yeah. Yeah. Of course, this is a barrier to flow. Ya. Jadi sistem throttle governing ini menimbulkan hilang tekan. Okay, so this throttle governing actually imposes an increased pressure drop to the steam flow. So some work will eventually lost through this governing mechanism. Okay. Right. Now, again, I'm not going to go through a lot of detail, but this talks about a very mechanical issue. Okay, so this talks about how you can control the steam flow rate. Okay, therefore, I will not go to a lot through these equations. Okay, suffice it to say that okay, hang on a second. Yeah, so each turbine have their own value of this constant C and M sub 0. Okay, so M sub 0 is a steam rate that occurs without any load to the turbine. Okay, and C is a constant. We call it a comparison constant. Yeah, konstanta pembanding. Okay, so M without sub-zero is the steam rate at various loads. Okay, so this is what we calculate. Okay, and M sub-zero is provided usually in the problem. So we know this from the design of the turbine, from the specification of the turbine, we know the steam rate without load. Okay, and W is the load. So the W can be changed, and M will follow whenever we change the load of the turbine. Okay, and C is just, this is a constant. It's not it's probably more correct stated as proportionality. There we go. Proportionality constant, ya. Konstanta pembanding. Jadi dalam permasalahan perhitungan throttle governing ini, laju kukus ya, steam rate, ini sering dianggap berbanding lurus dengan beban. Ya. Nah, persamaan linear ini sering disebut juga dengan Wheelen's line. So Wheelen's line refers to this linear equation. Okay. M0 ini adalah laju uap tanpa adanya beban. Ya. Jadi loss saja gitunya. Poros generator itu loss saja, nggak ada beban. Oke. Sementara W ini adalah beban. Ya. Beban kerja turbin yang bisa dinaik turunkan. Dan C adalah konstanta pembanding. Gitu aja ya. Jadi rumusnya gampang sekali. Oke. Then you can follow the rest of the formula. Yeah, Kevin.
Sir, how do you add load to steam, sir?
By manipulating the governor. So you can think of governor as a steam, as a control valve for steam rate, for steam flow rate. But that's a good question actually. It's a very good question. It is something simple, but when you think about it, it's not as easy as that to answer that question. Okay. Okay. Of course, in the reality is not as simple as my words. So in an actual power plant operation, there's a mechanism that that tells the operator that they need to increase electric power production or to decrease electric power production. Yeah, I'm not an electrical power guy, so I don't know how to control that. But anyway, jadi dalam kenyataannya itu jauh lebih rumit daripada omongan saya tadi. Ya. Nah, kalau dalam power plant, steam power plant itu jika terjadi misalkan gini, misalkan malam hari kemudian kebutuhan listrik naik gitu ya. Nah, di sisi pembangkitan listrik itu ada mekanisme untuk mengetahui bahwa electrical demand-nya sedang naik. Oke, kalau electrical demand-nya naik, maka boiler dan steam turbine harus beraksi, harus mengikuti kenaikan tersebut. Okay. Now, how that happens, to be frank, is beyond my knowledge. Okay, it's in the realm of electrical power engineering. Suffice it to say that there's a connection between the electrical generation side and the steam turbine side that communicates with each other through this control mechanism. Okay, but if we just look at the steam turbine point of view, then the controlling action, yeah, is to change the opening of the governor. Ya. Jadi ada sistem yang mengindra bahwa kebutuhan listrik sedang naik atau sedang turun, itu kemudian diterjemahkan menjadi controlling action. Ya. Next semester you will learn about controlling action in a control system. And the controlling action is this governor, which increases or decreases steam flow rate.
Sir, one more question, sir.
Yep.
Just now you said that when you decrease the rate, then like the efficiency will decrease as well, right, sir? Or if you, or the rate is too high, it will also decrease the efficiency, right?
Yep.
Like, is it possible where like you keep the rate equal or like constant so that the efficiency will always be the same? But then if you need less, is there like a storage for electricity or something, sir?
Okay. Yeah, it's actually a very good point, and yes, there is to some extent. Again, I'm not a electrical power engineer by any means. Okay, but yes, actually there are ways for these major power plants to store electricity somewhere, especially if they're tied to a grid system. Yeah. Now, for example, maybe have you guys ever heard of jaringan listrik Jawa Madura Bali, Jamali? Anybody have heard of it? Maybe read about it?
I don't think so.
Okay. All right. So in fact, the Isles of Java, Madura, and Bali are interconnected to each other. Okay, in terms of their electrical grid. So it's like a load sharing. It's a load sharing network sort of thing. Anyway, so along this massive power grid, there are ways to store excess electric power, and those are called capacitors. Okay, so you don't imagine the capacitor to be tiny like you have in your radio or your computer. These are huge, humongous sized capacitors. Okay, and the purpose of capacitor is to store electrical charge, just like we do in our chemical processing plants using storage tanks. Okay, so there are several devices by which you can store excess electricity. Batteries are also those are also used to store excess electricity. Okay, jadi good question ya. Jadi ada beberapa komponen di dalam jaringan elektrik dalam power grid ini ya, yang bisa menyimpan ekses tenaga listrik. Ya, secara umum namanya kapasitor. Nah, kadang-kadang kalau gede namanya kapasitor, kalau agak kecil namanya baterai dan sebagainya ya. Tapi basically ini adalah alat-alat yang memang memiliki kemampuan untuk menyimpan tenaga listrik, gitu ya. So for those of you who are doing your research in Pak Hardev's lab, they usually deal a lot with these devices, with capacitors. Okay, so just to give you a background, if you happen to do your TA in Pak Hardev's lab, so a capacitor is a device that can store electrical charge, and it can release them as needed, just like storage tanks. Yeah. All right. Any other question, Kevin?
All good, sir.
Okay, thanks. All right, so moving on. What happened to the graph here? Okay. There we go. That's much better. All right. The second type of governing is called a bypass governing. This is often done with extraction turbine. So now remember, you should remember what extraction turbine is, okay? Turbine ekstraksi. So extraction turbine is any turbine that enables us to extract steam from between these stages. Yeah, just like this. Okay, so you can see that, here in the first stage, we have a portion of the steam, usually a minor portion of the steam is tapped out, is extracted out of the turbine for some other purposes. Okay, now this extraction line can also be used to regulate steam flow. Okay, so for example, if the turbine needs less flow, then this extraction flow rate can be increased. Conversely, if the turbine needs more flow, then this bypass flow can be reduced or even closed altogether. Okay, so this is called bypass governing. Okay, so again, in my defense, I'm not the one who's doing the translation. Okay, sorry about this. This is bypass, not shortcut. Jeez. Okay, so bypass stream is a steam exiting turbine at certain expansion level. This one here. Okay, this is called an extraction stream or bypass stream. Okay. Again, you can use this for any other purpose. For example, you can use this steam for heating purposes, for example. Okay, but again, you can also return some of the bypass steam back to the turbine as a way to control the steam flow rate. Okay. Yep. Easy here. This is the bypass control valve. Okay, so if this valve sense that we need to increase the load, for example here, okay, so if we need to increase the load of the turbine, then this bypass valve will open. So that will create the effect of that opening is that more steam will return to the turbine as opposed to be extracted out of the turbine, right? Conversely, if we need to decrease the load of the turbine, then this valve will close. Okay, and you see if this valve closed, then the amount of steam going here will reduce. And the amount of steam going this way will increase. Okay. So this is also a nice way of being able to control the flow rate, the steam flow rate of a turbine. Okay. Okay, there's some other problem, and I will leave this to our assistant, to Zefa, to discuss it with you guys. Okay. Let's have a 5-minute break. If you guys need to go to the bathroom or to drink some water or something, so let's take 5, and we will restart again at, we will reconvene here. We'll continue at 4. Okay. Let's just a little bit more about the steam turbines. So here are some practical examples of them. Oh, sorry about this overly large table, you guys. There we go, that's more like it. Okay, now these are just to give you some idea, some numbers, okay, to give you an idea about the magnitude of specifications of these turbines. So these are examples that were collected by Heri from his trips. His his consultative projects, I believe. So we have, for example, here there's a CPO plant, okay, crude palm oil plant, or some people call it oil, palm oil mills. Okay, so PP is called a back pressure turbine, and this is the nameplate capacity. Okay, the specified capacity of the turbine output. This is the RPM, the rotational speed of the turbine. This is the specification of the inlet steam and the outlet steam. Okay. Now, one thing to keep in mind is the especially important numbers for you guys is this one here. Okay, inlet steam conditions, and also the power. Okay. Let's see what else. Okay, now the inlet steam pressure and temperature will determine the boiler condition. Okay, so and I will show you in the next chapter that specifying the temperature and the pressure of steam boiler is perhaps one of the most important work in the design of the steam system. And that condition, okay, the steam pressure and temperature as generated by the boiler is oftentimes dictated by these numbers in the steam turbine. Okay, so now imagine that you want to design a steam system, okay, that includes a steam turbine whose steam specification is like this. Then, of course, for example, here, okay, if the CPO plant calls for a steam pressure of 19 kilogram force per centimeter square and a steam temperature of 260 degrees Celsius, then your boiler should be not too far from these numbers, right? So your boiler steam production pressure and temperature will not be too far from this one. Okay, 19 kilogram force per centimeter square and 260 degrees Celsius as a steam temperature. Okay, maybe slightly higher to account for losses in the piping. Ya, oke. Jadi saya ulangi dalam bahasa Indonesia ya. Jadi sangat penting bagi kita untuk memahami, mengetahui tekanan dan temperatur steam, inlet steam di dalam turbin. Karena ini akan menentukan kondisi produksi steam dari boiler. Kalau boiler yang kita rancang itu hanya melayani steam turbine, atau steam turbine ini adalah unit yang kebutuhan tekanan dan temperatur steamnya paling tinggi di dalam sistem kita, maka dialah yang menjadi penentu rancangan boiler. Okay, so throughout our entire steam system, if the steam turbine has the highest steam pressure and temperature, then the steam turbine will determine the overall condition of the boiler output. It will determine the boiler pressure and the boiler temperature, right? I think that makes sense. Yeah? Okay. Now, that may not be true if you have any other unit within your steam system that requires steam at an even higher pressure and or temperature compared to your steam turbine. Okay. And here's some terminologies here. So PP is spec pressure turbine. Check back your notes about what that means. ECT, extraction condensing turbine. CT is condensing turbine, and EBT is extraction back pressure turbine. So whenever you hear the word extraction turbine, so please keep in mind that it means the turbine generates steam at its intermediate stage. Okay, so turbine invariably consists of more than one expansion stage, and in between those stages we can install a steam tapping line, a steam extraction line. Ya, jadi turbin itu biasanya terdiri dari lebih dari satu tahap, terdiri lebih dari satu tahap ekspansi. Dan kalau di antara tahap-tahap tadi kemudian kita pasang jalur untuk mengeluarkan sebagian kecil dari steamnya, maka itu namanya adalah turbin ekstraksi, extraction turbine. Okay. All right. So, and here's some more examples. Just feel free to look at it at your own leisure. I'm not going to go through each and every of those steam turbines. Okay. Examples of steam turbines for large industries such as petroleum, is not oil. Petroleum and natural gas refineries. Steam turbines are used as power plants or compressor driver. Okay, so you can use them as a power generator and or as driver. Okay, as a direct driver. Okay. And these are the steam turbines operated by PT Badak. Okay. This is the one that I mentioned before. They have several huge steam turbines to drive the refrigeration system compressor. Okay, so these are huge. These are really big turbines. Yeah. Okay. All right. Okay, some more examples. I'm going to skip that. What is this one here? Okay, increasing cycle efficiency. Yeah. Again, we will go through this in our responsive session. Okay, this is a problem example. You can read about it yourself, but we will give you another session with the assistant to sort of guide you step by step through these calculations. Okay. Okay. So some of the calculation in the exam problem will be something like this. Maybe not as long as this, but some of them will be, will involve calculations like this. Okay, so what happened here is actually, this is what is called a cycle analysis. Ya, jadi ini dinamakan dengan analisis siklus thermodynamic. So essentially, what you do here is you first you start with the analysis of a baseline cycle. Ya, jadi kita memulainya dari analisis efisiensi termodinamik suatu siklus dasar, ya, keadaan dasar, and then we vary the condition of several process variables. We can perhaps change the boiler pressure, we can change the steam temperature, or or both of those variables, and then see what happens to the cycle efficiency. ya. Jadi dalam analisis siklus seperti ini biasanya dilakukan pertama-tama adalah menghitung efisiensi dari siklus dasarnya, dari keadaan dasar. Ya. Kemudian kita mengubah-ubah beberapa variabel, misalnya tekanan boilernya, temperatur boilernya, atau dua-duanya sekaligus kita manipulasi dan kita lihat bagaimana pengaruhnya terhadap cycle efficiency. Okay. So that kind of analysis will give you a good idea of what's going on in the actual operation of the steam system, of the steam turbine. What happened if you change the pressure, if you increase or decrease pressure, then what happened to the efficiency, what happens to the steam rates, and so on. Okay. Okay, more detailed discussion will be done, will be guided by the assistant. Okay, don't worry about it. Okay, and this is a recap of the results from efforts in increasing cycle efficiency. Okay, so steam pressure increased from basis. Yeah, sorry, steam temperature increased from basis. Sorry. Okay, and you can see this is the baseline condition, right? That's the baseline condition. So in the baseline condition, the cycle efficiency is 20.5%. And then when we increase the steam temperature, okay, so steam temperature is increased from 225 degrees Celsius to 250 degrees Celsius, then the cycle efficiency is increased from 20.5 to 20.6%. Okay, this one here. Yeah. You can follow the calculation from the previous pages. Yeah. The next one, we increase steam pressure from the baseline value. So the baseline value is, what is this one? Okay, 1800 kilopascals increased to 2000 kilopascals. That increases the efficiency from 20.5 to 21.13. Now, you cannot really predict these numbers without performing the calculations. Yeah. Jadi kita tidak bisa memprediksi berapa perubahan efisiensi yang akan terjadi tanpa kita melakukan perhitungan. Ya. Dan perhitungan-perhitungannya bisa kalian lihat di halaman-halaman sebelumnya. Okay. Let's see what else we have here. Decreasing condenser pressure. Okay, decreasing condenser pressure from the basis. So in the basis, the condenser pressure is 100 kilopascals, and this is decreased to 50, okay, to 50 kilopascals, and we see an increase in efficiency from 20.5 to 23.4. That's one. Okay, so we have 1, 2, 3, 4. Okay, 4 measures to increase cycle efficiency. Yeah. Right. Now imagine that you do this calculation using a range of numbers. If you notice, right, what we do here is just 1-point calculations. So we change the steam pressure by just one value, right? We change it from steam temperature from 225 to 250. So that's just one number, okay, one step change. Here also in the steam pressure, we change the steam pressure from 1800 to 2000. Okay, again, we're only changing it by one number and so on. Now, of course, you can do this using many variations. Okay, and if your variations is large enough, then you can construct some sort of graphical representation of the thermodynamic efficiency, so you can pinpoint which combination of condition will give you the optimal, the highest thermal efficiency. Yeah. Okay. Oh, okay, so that's the end of the current chapter. Any questions here? All right. Now, if not, I will move on to the next chapter. Okay, as usual, let's take a 5-minute break when we move to the next one. Oh, yeah. So the next chapter is steam system balance. Yeah, neraca system 1. Okay, let's do 5-minute break and we will return at 4:25. Okay, 4:25. This will not be a thorough review of the chapter, but I will probably go through about a quarter of this chapter, of this rather long chapter, to give you an idea of what a steam system look like, what are its basic components, and its the principles of how it works. Okay, so we'll meet again at 4:25. Okay, 5 minutes break. Let us continue with the next chapter, which is the steam system balance. Share that. Okay. Yep. Why is not there? Okay, so the part one is the talks about the overall design of steam systems. Okay, so a steam flow diagram, okay, or steam utility flow diagram consists of steam condensate and steam flow rate, steam pressure, steam temperature, steam enthalpy on work produced by the turbine. Okay, typically it shows these variables, and also contains equipment used in the steam system, which is divided into steam consumers, which uses steam as the source of thermal energy. So these would be the processes that require thermal energy in the form of steam. Okay, any process equipment, for example, a reboiler. Okay, distillation tower reboilers. That's an example of steam consumer. Steam turbine, and many more. Okay. Then second one is the boiler or the steam generator, which include waste heat boiler. Okay, we'll talk a little bit more about this technology later on. The turbine, okay, so back pressure condensing and extraction turbine. Letdown station, okay, letdown station for decreasing steam pressure to more suitable condition, usually consists of PRV or pressure reducing valve and a DS or desuperheater. Okay, so again, a letdown station in a steam system, a letdown station's purpose is to decrease steam pressure. Pure and simple. Okay, and the next one is the aerator or DA and boiler preheater. Okay, the reason why we need a aerator is because the presence of air in a boiler feed water, of course, can cause severe corrosion problem. And the higher your boiler pressure is, which means your boiler runs at higher temperature, the probability of occurrence of corrosion from impurities dissolved in water will increase tremendously. And one of the most notorious impurity in water is actually dissolved oxygen. That's why we need this deaerator unit within the steam system. Okay, and last but not least are the steam headers and condensate lines. Okay, and I will show you in a few minutes what these look like. Okay, so steam system diagram based on the type of equipment is easier to arrange than ladder diagram of steam pressure. This one might not make sense now, but it will make sense in a few minutes. The equipment is categorized by its type and further arranged according to the steam pressure. Okay, the equipment is pictured with named square figure. Okay, like this. Okay, so this is called a steam flow diagram, or some people call it a UFD, utility flow diagram for steam. Okay, so these are the steam generators, the boiler. Ya, jadi ini adalah unit pembangkit steam. Okay, process steam generation. This will be the waste heat boilers. Okay, so the difference between this one and the boilers is that the source of heat from process steam is not fuel combustion, but it's excess heat from the process stream that is used to generate steam. Okay. Okay, and this one is HPIP, meaning high pressure and intermediate pressure turbines. Okay, So a turbine will consume steam and it ejects. So if you see this type of diagram, okay, this tells you that the turbine is a non-condensing turbine, because you can see the steam is returned to the steam header. So these are called headers. Okay, we have three headers in this diagram: high pressure, intermediate pressure, and low pressure headers. Yeah. Let's see what else we have here. Now these are condensing turbines. Okay, high pressure condensing turbine. So the output of condensing turbine, remember, the output is water, it's not steam. So you cannot return this stream to the header. So this stream has to go back to the PFW supply system. Okay, so because this is liquid water, this is condensate, so it has to go to the aerator and then return to the boiler. Okay. Right, so let's see what else we have here. These are the high pressure steam consumers, meaning this is catch-all terms for any process unit that are not turbines. Okay, so we call those steam consumers, high pressure steam consumers. And because the steam is utilized as a heating media, then it is safe to assume that the steam exiting the consumer is not in gaseous state, it is in liquid state. Okay, and therefore the output of the steam consumers goes here to the PFW line, okay, to the boiler feed water line, right? Okay, and this is a loss, meaning this is a purge line, ya. Jadi ini jalur purging, jalur pembuangan, ya. Remember that any continuous chemical processing process has to involve some way to purge impurities, okay, out of the system, and this is the purging line. Ya, ini jalur purgingnya. Okay, now let me repeat this in Indonesian, okay, just to make it clear for you guys. Ya, jadi kalau kita lihat dari kiri ke kanan, ini adalah pembangkit uapnya. Ada dua sistem pembangkitan uap, yaitu boiler dan proses steam generation. Boiler kan sudah tahu ya. Yang sebelah kanannya ini adalah pembangkitan steam menggunakan excess heat, menggunakan panas yang terbuang dari proses. Ya. We also call it waste heat boilers. Oke. And here, yang sebelah kanannya ini adalah turbin-turbin, ya, unit-unit turbin. Kalian lihat di sini ya, jadi steamnya masuk dari atas, kemudian keluar ke sini lagi ya. Nah, ini artinya tidak ada steam yang terembunkan. Jadi ini adalah non-condensing turbines. Okay, so all of these are back pressure turbine. Okay, high pressure, intermediate pressure, back pressure turbine. Kemudian di atas ini ada 3 header. Ya, ada 3 pipa utama yang berisikan steam. High pressure header, intermediate pressure, or sometimes I think it's more popularly called as MP header, medium pressure, instead of IP or intermediate pressure. Okay, so jadi di atas ini ada header tekanan tinggi, tekanan menengah, dan tekanan rendah. Okay, header ini pipa yang ukurannya relatif besar, ya, yang digunakan sebetulnya sebagai semacam tangki penyimpanan steam juga, ya, tangki yang berukuran nggak terlalu besar gitu. Intinya adalah header ini jalur utama penyaluran steam, ya. Oke. Jadi yang terjadi di dalam turbin back pressure ini adalah mereka mengambil steam dari high pressure header, kemudian steam yang keluar dari turbin-turbin ini dikembalikan lagi ke header. Tetapi tentunya tidak bisa dikembalikan ke high pressure lagi. Dikembalikannya bisa ke medium pressure header atau ke low pressure header, tergantung dari bagaimana spek kerja turbin ini. Oke, terus yang berikutnya di sini adalah condensing turbines, ya. Artinya steam yang keluar dari turbin ini kondisinya bukan uap, tetapi kondisinya adalah cair, sehingga dia nggak bisa balik ke steam header, tetapi harus masuk ke jalur pengolahan boiler feed water, BFW. Ya. Jadi dia masuk ke unit di aerator di sini. Oke, nanti dia akan diolah bersama-sama dengan make up boiler feed water, dihilangkan oksigen terlarutnya, dan kemudian diumpankan ke boiler. Ya. Oke. Nah, sebagian dari aliran uap, sebagian dari aliran uap dan aliran air ini juga dibuang ya untuk mencegah penumpukan pengotor di dalam jalur. Karena di sini kalian lihat banyak recycle-nya ya. So as you can see, the whole system involves quite a lot of recycling, okay, recycled streams. So just in any other recycled streams, we need to have a purge line to avoid the accumulation of impurities. Okay, and the one that is purged is typically the liquid water. The condensate is being purged, not the steam. Ya, jadi biasanya yang di purging itu ke lingkungan itu bukan steam, tetapi air. Ya. Okay, so we have here, so these are other steam consumers. Okay. Nah, oh ya, ini saya ulangi dalam bahasa Indonesia ya. Jadi yang dimaksud dengan steam consumer ini adalah istilah umum untuk apapun unit di proses yang mengkonsumsi steam untuk pemanasan. Not for motive steam, but thermal steam. Ya. Karena steamnya dipakai untuk memanaskan, maka kita bisa mengasumsikan keluarnya bentuknya bukan berupa uap, tetapi berupa cairan yang dipakai kan panas latennya. Ya. Karena keluarnya berupa cairan, maka dimasukkannya ke jalur BFW. Ya. Setelah sebelumnya di sini ada flash drum, ya, oke. Apa yang dimaksud dengan flash drum di sini? Kegunaannya apa flash drum di sini? So, what is the use of flash drum here? Now, the water exiting, the condensate exiting the steam consumers is still perhaps in a high temperature and high pressure. Okay, the pressure is still too high to be introduced or to be integrated with the makeup flow here. Okay, so we need to reduce its pressure. Now, as we reduce the pressure, some of the steam will flash out. Ya, jadi pada saat kita mengurangi tekanan dari aliran air yang masih temperatur dan tekanan tinggi ini, sebagian dari uap air akan menguap di dalam flash drum. Nah, uap yang memisah di dalam flash drum ini dikembalikan ke header. Okay, and the rest of the condensate, which has been reduced, the pressure of which has been reduced, is collected in the aerator here. Okay, so this is what's happening in this steam system. Okay, so this is a steam distribution and steam generation system. Okay, so, and we have this condensate storage to store the water condensate. This is a fin fan cooler condenser. Okay, so this unit condenses excess steam using air cooling. Ya, jadi ini adalah kondenser untuk mengembunkan sisa-sisa uap yang mungkin masih terkandung di dalam kondensat, ya, supaya tuntas pengembunannya didinginkan dengan menggunakan kipas, ya, dengan pendingin udara. Okay, and we have several. These are let down stations. So these are the equipment that reduces the pressure of steam from high pressure to medium pressure, from medium pressure to low pressure. Okay, yeah. Now, take a look at the boiler. Okay, so the boiler in this case produces steam at what pressure? Boilernya memproduksi steam pada tekanan apa nih? Masuk ke header mana nih?
High pressure, sir.
Yep. So it produces steam at a single pressure, which is the high pressure. Now, this is a very typical design, okay, because it gives us the maximum economy. Yeah, it doesn't really make sense. Now, of course, if you all notice that we have three pressure headers, right? We have high pressure, medium pressure, and low pressure headers. But it doesn't mean that you need to have three boilers. It doesn't make sense at all. Okay, so what makes sense is to produce the steam at its highest temperature and pressure, and then let it down, and then let down the pressure to produce the medium pressure steam and the low pressure steam. Okay, ya, jadi hal yang biasa dilakukan di dalam rancangan sistem steam adalah memproduksi steam di boiler pada tekanan dan temperatur setinggi mungkin. Kalau bisa satu kondisi aja, ya, kondisi high pressure-nya, Kemudian jika kita memerlukan kondisi tekanan menengah dan tekanan rendah, ini tinggal di let down saja, diturunin tekanannya. Oke, it makes much more sense than having one boiler for each header. Okay, unless your steam requirement is such that the high pressure steam requirement is much smaller than the lower pressure steam. Yeah. In that case, you might need two boilers. Okay, one for high pressure surface, high pressure low load process surface, and the other one is for low or intermediate pressure. Ya, jadi memang secara umum lebih ekonomis kita menggunakan satu boiler aja. Satu boiler membangkitkan pada tekanan tinggi, pada tekanan dan temperatur yang paling tinggi yang dibutuhkan pabrik kalian. Tapi bisa saja pabrik kalian itu kebutuhan alokasi steam tekanan tingginya kecil. Yang lebih besar adalah steam tekanan rendah dan tekanan menengah. In that case, ya, mungkin bisa jadi kalian terpaksa menggunakan dua boiler. Satu boiler yang berukuran kecil, ini digunakan untuk temperatur untuk tekanan tinggi, dan boiler yang tekanan yang lebih rendah, tetapi ukuran yang lebih besar, itu digunakan untuk melayani steam tekanan rendah dan tekanan menengah. Gitu. Okay. So in other words, this is a typical design, but it doesn't have to always absolutely follow this pattern. We have to be flexible. Okay. Because it doesn't make sense. Okay. It also doesn't make sense to produce steam at the HP condition when its usage is very small compared to the intermediate pressure and the low pressure. In that case, we have to have two separate boilers. One high pressure boiler, and the other one is a medium pressure or perhaps a low pressure boiler even. Yeah. But if the need is balanced, ya, kalau kebutuhan steamnya antara tekanan tinggi, tekanan menengah, dan tekanan rendah itu lumayan balance, ya, kuantitasnya mirip, maka lebih make sense boilernya hanya memproduksi satu jalur saja, yaitu pada jalur tekanan tinggi. Okay. Because we generally do not compress steam. Okay. Steam is a rather nasty fluid to be compressed. Okay. So jadi biasanya tidak lazim ya kita memproduksi steam itu pada tekanan rendah, kemudian kalau butuh tekanan tinggi steamnya dikompresi. Steam itu fluida yang nggak terlalu bersahabat terhadap kompresor, ya, korosif lah dan erosif dan sebagainya ya. Jadi biasanya kita tidak mengkompresi steam. Steam itu diproduksi di boiler pada tekanan setinggi mungkin, kemudian diturunin secara bertahap sesuai kebutuhan. Okay. So steam, water vapor is aggressive to compressors. Yeah. So we typically do not compress steam, but we produce steam at the highest possible temperature and pressure, and then reduce the pressure gradually as needed. Okay. Right. So that's the reason why if your high pressure steam is lower, the requirement is lower, significantly lower than the intermediate steam or lower pressure steam, we do not produce steam at lower pressure and then compress it. Okay. But we use two separate boilers typically. Okay. All right. Any other questions? All right, if there is any question, we will continue next week with discussion on steam system, okay? And in the meantime, Pak Hendra, perhaps you can coordinate with Zeva to schedule the responsive session for the students, okay?
Okay, Pak Meki.
And she can use the example problem that's already in the handout to discuss. or if you want to put together another exercise problem, that's fine too.
Oke, Pak.
All right, thank you very much, and we'll see you all next week. Okay, stay healthy and safe, you guys.